Hello friends, in this video we're going to present the quantum mechanics of hydrogenic atoms. And by hydrogenic we mean atoms that contain just two particles from a chemistry standpoint, a nucleus and an electron, and just a single electron. So hydrogenic atoms are atoms that just have one electron. So, what are we going to talk about? So the first thing we're going to do is we're going to determine the Hamiltonian operator for this one electron system. And from that we'll look at the Schrödinger equation and the solutions to the Schrödinger equation, which include the wave function corresponding to the one electron system and the quantum numbers that result from that one electron system, which we'll find, as you might already know and suspect, quantized energy. So what is the Hamiltonian? Well, we use in this case what's called a center of mass coordinate system, center of mass between the nucleus and an electron. And of course, in the case of the hydrogen atom, that nucleus contains a single proton. And we're going to look at, from this, the energy, or determine the energy for the electron nuclear system. All right, so we have our general form for the Schrödinger equation here, which shows the Hamiltonian operator operating on our wave function to generate the energy times the wave function. And of course, what we're trying to determine here is the wave function with the corresponding energies for the various wave functions that solve the equation. So what is the Hamiltonian operator? The Hamiltonian operator, of course, includes a kinetic energy term, as we've looked at in the past, and the potential energy term. So the potential energy term must include the Coulombic interaction between the positively charged nucleus and the electron. So in this term, of course, we have the atomic number Z. Okay, it's because we are talking about hydrogenic atoms. For hydrogen, of course, Z is equal to 1, but we could be talking about, for example, helium plus, which would have a single electron, but the atomic number would be 2. Then we have E here in the numerator, which corresponds to the charge of an electron, the elementary charge, and in the denominator 4 pi epsilon naught being a constant referred to as permittivity, and R here in this equation corresponding to the distance between the electron and the nucleus. So the overall Hamiltonian is given by our kinetic energy term represented here, where mu is a reduced mass for the nuclear electron system, and the potential energy term here. And again, notice that it is negative because we have an attractive interaction between the nucleus and the electron, and that attractive interaction corresponds to a negative potential energy. Here, of course, is the equation for reduced mass, which we have talked about previously, having the same form as our previous discussions of reduced mass. So, because our system has a potential energy which depends only on the distance between the nucleus and the electron, it's actually best to use spherical polar coordinates when solving the Schrödinger equation, and we will get a wave function in terms of spherical polar coordinates. Here is, in fact, the Hamiltonian when we do the conversion from x, y, and z to spherical polar coordinates for the hydrogen atom. When its potential energy term has a z value equal to 1, so this would be the equation for the hydrogen atom. We're actually not going to solve this, of course, but I just thought I'd show it to you just for giggles. All right, so when we do this, we get what's called a separable equation, which means that the wave function, which is a function of our spherical polar coordinates r, theta, and phi, is a product of functions of distance, theta, and phi. Now, as you'll recall from a previous discussion of three-dimensional rotational motion and spherical polar coordinates, that this part of the wave function corresponding to theta and phi can actually be combined into our spherical harmonics And so it has the same form as the spherical harmonic. So we can actually express the wave function for the system as a product of a function which is called the radial function, because it's only dependent on the radial coordinates, and the spherical harmonics. All right, so just a reminder, when we look at our spherical harmonics, as in our previous discussion, we find that our spherical harmonics will actually give us, remember we have their spherical harmonics which have quantum numbers L and m sub L, and where spherical harmonics are going to give us the s orbitals, as we'll recognize from general chemistry, when the quantum number L is equal to 0, the m sub L quantum number is equal to 0, we have a spherical shape, and that of course is our s orbital. When we have a quantum number of L equal to 1, and we have m sub L quantum numbers of -1, 0, and +1, then we get the p orbitals. Of course, we get 3 p orbitals corresponding to different directions, the px, the py, and the pz. Now, I will add here that when m sub L is equal to 0, that corresponds to the pz orbital, but the px and the py orbitals are not, strictly speaking, do not correspond to m sub L equal to -1 or +1 specifically. And that's something that we won't go into detail here as we discuss this. What we'll just simply note is that when L is equal to 1, there are 3 different m sub L values, and we get 3 different p orbitals as a result of that. The other thing to note is that the colors here in this particular diagram represent the mathematical sign of the wave function in those regions, so that we have one region which has a positive sign and another region which is differently colored, which has a negative sign. It is important to note that these positive and negative signs do not correspond to electrical charge. That is very important to note. It is just simply the mathematical sign of the function. So in the region of space indicated by blue here, the sign of the mathematical function is positive. When it's red, the sign of the mathematical function is negative. And now we have the d orbitals shown here, where the d orbitals correspond to L equal to 2 with 5 different m sub L values. So we have 5 different d orbitals. When m sub L is equal to 0, that corresponds to what we refer to as the dz squared orbital. But again, just as in the case of the p orbitals, the values of ±1 and ±2 do not correspond to specifically to any of the remaining orbitals. They're what we call linear combinations, and that's something that we'll perhaps talk about a little bit later. Again, noting signs here, we'll note the different lobes of the orbitals correspond, the different colors correspond to different mathematical signs. In this case, for the dz squared, we see the 2 lobes above and below the xy plane. The dz squared orbital is oriented along the z-axis, so the blue region represents about the xy plane. So above and below that, we have a negative sign in this depiction and a positive sign within the plane itself. Now, we obviously have a situation here where we have quantum numbers. We've already talked about the orbitals. We know from our discussion of spherical harmonics that we have the L and the m sub L quantum numbers. But when we do the solution for the atomic system, we actually get 3 quantum numbers here, different types of quantum numbers. We have n, the n quantum number corresponding to what we refer to as the principal quantum number, the L quantum number, and the m sub L quantum number. And so we'll note there are limitations. For example, the L quantum number has a maximum value of n-1. The m sub L quantum number has the same restrictions as what we referred to earlier. It ranges from -L to +L. So when n is equal to 1, when our principal quantum number is equal to 1, we'll note because of the n-1 limitation, the only value of L that's possible is L equal to 0. And of course, based on our limitation there, when L is equal to 0, then m sub L is also limited to being equal to 0. And that is then corresponds to what we refer to as the 1s orbital. the 1 of course referring to the principal quantum number. When n is equal to 2, we note that the limitation here is that for L, which ranges from 0 to n minus 1, L may be equal to 0, and that means m sub L is equal to 0, and that of course corresponds to 2s. So L equals 0 will always correspond to the 2s orbital. We also note that when n is equal to 2, L may be equal to 1. Again, noting this particular condition that we can have a maximum value of n minus 1. And again, remembering that when L is equal to 1, we have m sub L values of negative 1, 0, and plus 1, which correspond to the 2p orbitals as we noted earlier. When n is equal to 3, we can have L equal to 0, 1, or 2. All right, and again, we have the same limitations as before. When L is equal to 2, we have the range from negative 2 to plus 2, which of course then corresponds to L equals 0 is a 3s orbital, L equal to 1 is the 3p, and L equal to 2, of course, is the 3d. And so this limitation, of course, is why we can have a 3d but not a 2d, because the d orbital corresponds to L is equal to 2, and our limitation here is n minus 1. We cannot have a 2d orbital because the maximum value of L for the 2d orbital is equal to 1. We can't have L equal to 2. All right, so here's kind of a summary then of our solutions to the Schrodinger equation. First of all, as we've already discussed, we have our wave function, which of course depends on the radial component, which we'll denote here as r n sub L, because it turns out the radial component depends on both n and L. And this is something we'll get into detail later about the specific function for the radial component. And we have spherical harmonics, which depend, of course, on theta and phi, which you've already talked about that. So the spherical harmonics are going to give us the behavior of the wave function and the shape of the wave function as a function of angle. The radial component is going to tell us how the wave function depends on the distance from the nucleus. And then, of course, we mentioned quantized energy levels, so we do have quantized energy here. And this is the equation for the energy, where we're going to note again that here we have the situation where the energy is inversely proportional to n squared, n being the principal quantum number. You'll notice that the energy depends only on the quantum number n. It does not depend on L, and it does not depend on m sub L. So that means, specifically, that the energy of a 2s orbital is equal to the energy of the 2p orbital, because the energy depends only on the quantum number, the principal quantum number 2. Now that may seem odd because you learned in general chemistry the Aufbau principle and that the 2p orbital is higher in energy than the 2s orbital. How can that be? Well, we're going to find out in the next video that things change when we add more electrons to the system. Remember, what we're discussing here is for a one-electron system. So in one-electron systems, the energy of the 2s is the same as the energy of the 2p because the energy depends only on n. When we add additional electrons, we're going to throw electron repulsion into the mix. And electron repulsion is going to lead to a situation where we see that the 2s and the 2p orbitals have different energies. That's in a video to come, so stay tuned. The other thing that we'll note here when we talk about the energy, of course, is that we've got this constant here called a naught. That's the Bohr radius. It's just a collection of constants, and it's equal to 52.9 picometers. It's called the Bohr radius because this is the radius of the orbit calculated by Niels Bohr when he developed his model of the atom with orbits. We'll also note that the energy depends on the atomic number z and depends on z squared. So the higher the atomic number, the more negative the energy. And you will note this is important, that it is a negative energy that we're talking about here. So we note that as the principal quantum number goes up, the energy goes up. And again, remember, although the principal quantum number is in the denominator in this situation, because it's a negative energy, what happens is that as the principal quantum number increases, the energy becomes less negative. So higher principal quantum number, higher energy. We also have this simple equation here, which allows us, kind of puts everything into a simple situation. And again, this is for the case of hydrogen, where Z is equal to 1, all right, that the energy corresponding to a particular principal quantum number is negative 13.6 electron volts divided by n squared. So that's a simple way to calculate it, rather than having to deal with all these particular constants. For hydrogen, we can just use negative 13.6. Now, how might that change if you're dealing with, say, helium plus? In the case of helium plus, we're going to note that we have Z squared here. So for helium plus, when we do this calculation, we're going to note that Z is equal to 2. And so that means that the energy equation is going to become 2 squared. All right, and that looks like a Z, but that's a 2 squared. Let me erase that and try that again. And of course, in general, it's going to be Z squared. But in this case, it's going to be negative 2 squared times 13.6 electron volts divided by n squared. All right, so if we want to calculate the energy corresponding to a 1 electron system, we're just going to take the atomic number and square it and then multiply it by this. Now, if we remember our discussions early on about the emission spectrum of the hydrogen atom, we talked about the observation of the Rydberg equation that fit the data, and that was something that was derived by Niels Bohr in his model, orbit model of the atom. We'll find that because the Rydberg equation, which is given here, depends on 1 over n squared, that in fact the derivation from the Schrödinger equation actually is consistent with the Rydberg equation, and in fact we can derive the Rydberg equation for the emission spectra based on the energy equations for the atom. So this result from the Schrödinger equation is perfectly consistent with the observation of the emission spectra for these systems. Now, what else do we know? The energy is dependent on the principal quantum number. What do L and m sub L represent? Well, L and m sub L represent angular momentum, as we again talked about when we talked about three-dimensional rotational motion in a previous video. So just as before, the L quantum number allows us to calculate the total angular momentum of an electron. We'll note here that for the s orbital, with L equal to 0, that the total angular momentum for the s orbital is equal to 0. Which actually, of course, may seem odd if you're thinking about orbitals representing the motion, a circular motion, or some kind of angular motion about the nucleus, because any kind of angular motion is going to have angular momentum. So that kind of notion of a trajectory of an electron about the nucleus is not something that is consistent with the Schrödinger equation, and we really can't say anything about the trajectory of an electron. We will note that an electron that has L equal to 0, corresponding to s orbital, has 0 angular momentum. The m sub L quantum number represents a projection along the z-axis. And that means that it represents the component, the z component of the angular momentum vector. So if we draw a diagram representing these vectors, we'll see something like this. So that the vector here represents, the length of this vector represents the total angular momentum, and then the projection on the z-axis, which is represented here, has a length of jz. So that's what we're talking about when we talk about this. The L quantum number gives us the length of this vector here, all right, and the jz, the m sub L quantum number, allows us to calculate the length of the component along the z-axis. So that actually also, because it's the component along the z-axis, would actually allow us to calculate the angle with respect to the z-axis if we so desired. So that's what we find, is that the L and the m sub L quantum numbers actually represent a quantization of angular momentum. And again, the L and the m sub L quantum numbers do not affect the energy of the system, which means that we do have degeneracy in these systems as a result of that. So we've talked about the three quantum numbers, n, L, and m sub L. We've looked at the spherical harmonics, which give us the shape of the orbitals. Let's look at the radial component of the wave function, which gives its behavior as a function of distance from the nucleus. So this diagram here shows the radial components of the wave function as a function of distance from the nucleus. So that's what we have here. And we'll note the differences for the different types of orbitals. We'll note that for the s orbitals, the 1s, the 2s, and the 3s, that actually when the nucleus corresponding to a distance of 0, that they actually have maximum values at the nucleus. And that should actually cause you to ask some questions, because we know that that would then correspond also to a maximum probability of finding an electron at the nucleus. And you should be thinking, well, wait a second, the electron's not in the nucleus. There's no crying in baseball, and there's no electron in the nucleus. What's going on here? We'll see that that's the case for the s orbitals, not for the p orbitals or the d orbitals for that matter. That at the nucleus, for the p and the d orbitals, we'll find that there's wave function, the radial component is actually 0, so there's 0 probability of finding it there. So what the heck's going on here with the s orbitals, and how does that make any sense whatsoever? We can square the radial component, which of course you remember when we square it, it's going to give us a probability corresponding to at the nucleus. But again, we'll see the same thing. When we square it, the probability is maximized at the nucleus for the s orbitals. All right, but again, it's 0 for anything other than an s orbital. So how do we deal with that? Well, so here's the thing: is we're really asking the wrong question when we look at these particular diagrams, because what the radial component tells us is the probability of finding the electron at a point. Usually, we're more interested in asking the question, how does the probability vary with distance? All right, and so what that means is we're really asking about the surface area of a curve, because the nucleus corresponds to a single point. But as you move away from the nucleus and we're asking what's a probability at a particular distance r, then we have to think about a sphere at that distance r and all of the points on the surface of that sphere. So to get the probability of it being at a particular distance, then we have to include that idea, concept mathematically. And the way that works out is that we actually do something called the radial distribution function. If we take our radial component of the wave function and square it, and again, that's what we saw in the previous slide, but we multiply that by r squared, which is the distance from the nucleus, it turns out that what that does is it actually allows us to calculate the probability of finding the electron at a particular distance from the nucleus. Not at a point, but for all the points at that given distance. And so, if we want to know what the probability is over a range of distances. So suppose we want to know what the probability is of finding an electron between distance A and distance B. Then what we're going to do is we're going to integrate the radial distribution function over that region of space. And that's all we have to do. So now if we graph it, we'll see now when we talk about the s orbital, the 1s orbital, the 2s orbital, the 3s orbital, all the orbitals have a radial distribution function value of 0 at the nucleus. So the 1s orbital, what we're going to note is that the most probable distance is at this location indicated here. And we'll actually do a calculation later on to determine what that particular distance. So that means we're more likely to find the electron at this distance, at this maximum, than any other place. And you'll notice for the 1s orbital that we've got that situation where that distance is closer than many of the other orbitals, or at least closer than the maxima for other orbitals. We can also calculate the average distance, and the 1s orbital on average electron is going to be closer to the nucleus than any other orbital. We will note that, for example, if we look at the 2s orbital, there is a local maximum here that's close to the nucleus, but the global maximum, the real maximum, is farther from the nucleus than is the case for the 1s. One thing that's interesting to note is that for the 2p, the maximum for the 2p is actually closer than the maximum for the 2s, which also may seem kind of odd to you, but we'll talk a little bit more about that and the rationale for that and what that means later on. So this radial distribution function is what we're going to use to calculate probabilities associated with the electron at specific distances from the nucleus. And these are some calculations that we're going to be carrying out in the class. So this ends our discussion of hydrogenic atoms and the solutions to the Schrödinger equation for hydrogenic atoms. In our next video, we're going to be looking at multi-electron systems and how the solutions change when we add additional electrons to the problem. So stay tuned.